Alright, so for 48, they want you to divide. And so in order to do that, we have to multiply top and bottom by the conjugate of the denominator. Okay, so I'm going to put parentheses here. And the denominator is 4 plus 3i, so its conjugate is 4 minus 3i. And the numerator has to be exactly the same because this fraction has to equal 1. This one right here, always. So now we just distribute, so I get 24 minus 18i minus 8i plus 6i squared. In the denominator you get 16. Now remember, the middle terms cancel, so we're just left with minus 9i squared. Okay, and so I get, this here is minus 6, so 24 minus 6 is 18. And then these two right here is negative 26. And the denominator, this is plus 9 because of the I squared, so that's 25. So you just separate the two. 18 over 25 minus 26 over 25i. For 49, we can approach this by breaking up the i's into pair of i's. So for example, I to the fifth, you could see it as I, that's one pair, that's another pair, and then you have one left over. So every I squared, every pair of i's is negative 1. Like that, and then you have the I. So I to the fifth is negative 1 times I, which is I. And then I to the fourth, well, that's two pairs of i's, right? And so that's negative 1 times negative 1. So let me just write it out like this. That's one pair, that's another pair. So negative 1 times negative 1 is 1. And there's a coefficient 2, so that's going to be 2, just 2. I cubed we know is negative I. And then there's a negative in front of it, so that's plus I. And then I squared is negative 1, and then there's a negative in front of it, so that's going to be plus 1. So the real part is 2 plus 1. The imaginary part is I plus I, and there's the answer. So I've set up the polynomial in factored form. So here is the x minus 2 because the 2 is the 0. Then here's the 4 plus 3i. And remember, just like with radicals, the i's always come with a conjugate pair as zeros. Okay, they never come alone. So first I'm going to multiply these two, and then whatever I get here, I'm going to multiply by this. And that's going to be the final answer. Okay, so it's going to be equals x minus 2. I'm going to first distribute the negative. Minus 3i. And then I'm going to use a 3 by 3 to multiply these two together. See if they fit in here. So x minus 4 minus 3i, and then x minus 4 plus 3i. Multiply. So I get x squared minus 4x, 3xi, negative 4x, 16, negative 12i, then negative 3xi, 12i, and negative 9i squared. So 3xi and negative 3xi cancel out, that's 0. Negative 12i and positive 12i, that's 0. And then this number right here is negative 9i squared. It's actually, I squared is positive, it's negative 1, and there's a negative already there, so it's going to be a positive 9. Okay? So now, let me write it right here with black. I've got x minus 2 times x squared minus 8x. 16 and 9 is 25. So now I'm going to multiply these two together. Let's do it up here. I have some space. And so it's x minus 2, and then x squared minus 8x and 25. We multiply, that's x cubed negative 8x squared, x squared, 25x, negative 2x squared, 16x, and negative 50. Combine your like terms, so you get x cubed minus 10x squared plus 41x minus 50, and that's a polynomial. Alright, so number 51 does not factor by grouping, so we have to do the P over Q method. Now look at the list of p-values. It's huge, right? And the good thing is that Q is only plus or minus 1, so when you do P over Q, essentially you're just taking this list right here, because you're going to put all these numbers over 1, which, they stay the same. So because there's so many, I am going to set it up the way I set up the last synthetic division one, where I put the coefficients 1, 7, 32, and 60 up on top like that, and then I made a little chart. Now, the one thing I do want you to notice that all the coefficients here are positive, all of them. So it doesn't make sense to use the positive, the numbers in the positive side, because our goal is to get a 0. Well, if all of these are positive and I plug in another positive, I'm not going to get a 0. So I'm only going to use negatives, okay? This polynomial does not have any positive zeros, okay? Only negatives. If it has any rational, they're going to be negatives. So I'm going to start with negative 1. Bring down the 1. 1 times negative 1 is negative 1, plus 7 is 6. 6 times negative 1 is negative 6, plus 32 is 26, and again, this is not going to work. Okay, it's not 0. Let me go to the next one, negative 2. Bring down the 1. Negative 2 times 1 is negative 2, plus 7 is 5. 5 times negative 2 is negative 10. Plus 32 is 22, and then negative 44 plus 60 does not give me 0, so not going to work. Negative 3. Bring down the 1. 1 times negative 3, plus 7 is 4. 4 times negative 3 is negative 12, plus 30 is 20. 20 times negative 3 is negative 60, plus 60 is 0, finally. Okay, so we found a 0. And remember, once you have 3, I'd rather try factoring or use a quadratic formula, because the list is so long right here that would take so much more time. And then what if there are no more rational zeros, right? What if they're irrational? Then you'd be wasting your time. So this is x squared plus 4x plus 20. Now it doesn't factor. Okay, so then I wouldn't have found the answer anyway if I had done all the other negatives on the list. So this doesn't factor. I'm going to have to use quadratic formula. So it's going to be x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So that's negative 4 plus or minus square root of 16 minus 80 all over 2, which is negative 4 plus or minus square root of negative 64 all over 2. Now 64 is square root is 8, and then the square root of negative 1 is I. So then it's negative 4 plus or minus 8i over 2. Divide, factor out of 2. Negative 2 plus or minus 4i over 2 like that. So the 2's cancel out. And so the zeros, there's one real 0, negative 3, and then 2 imaginary zeros, negative 2 plus or minus 4i. Alright, so 52, we're finding domain, identifying if, seeing if it has any holes, vertical asymptote or asymptotes, horizontal oblique, and then I added the intercepts. Okay, so for the domain, we look at well, first of all, see if anything factors, but this one is prime. It does nothing factors in either the top or the bottom. The numerator denominator stays, are not factorable. So for the domain, we look at the denominator, and x could be anything because the zeros are imaginary. So the domain for this one is all reals. No restriction on the domain. The whole, since none of the factors, it had no factors that canceled, it has no wholes. And because the vertical asymptote is all reals, it has no vertical asymptote. Because the domain is all reals, it has no vertical asymptote. This one's power is equal, so it's a horizontal asymptote of y equals, look at the coefficients, 5 over 1, 5. X-intercept, you look at the numerator and ask yourself what makes it 0. Well, an imaginary number does, and so that one doesn't count, so it has no x-intercept. Y-intercept, you cover up all the x's. Okay, you cover up this one, and this one, and you're left with this. So it's 0, 8 over 9. Alright, so 53, we're going to factor it first. Okay, so the denominator is all x such that x cannot equal plus or minus 5 because that's what makes the denominator 0. We cancel this one, so that creates a whole. So the whole is at 5, comma. Now to find the y coordinate, remember after you cancel out the x minus 5, you're left with 1 over x plus 5. So you replace the x here with this 5 right here, because this is the x coordinate. So when you do that, you get 1 over 5 plus 5, so that's 1 over 10. Vertical asymptote, okay, since I still have that x plus 5 in the denominator, so x equals negative 5 is your vertical asymptote. This one's a bottom heavy, so it has a horizontal asymptote of y equals 0. It has no x-intercept because the numerator is not going to be 0 ever because there's only a 1 there. And the y-intercept, you cover up the x's, so in the final one there's only one x, so you cover up this one and you're left with 1 over 5. So it's 0, 1/5.